In this video, we're going to talk about series. Um, so the material on sequences is mainly as a setup for understanding series, which will be the main focus for the next two chapters. Okay, so before discussing series, let's review sigma notation. So this is a shorthand way of writing sums with a lot of terms. Okay, so suppose I write the following in sigma notation. So this is the symbol for sigma. It means summation. So suppose I have the summation from k equals 1 to n, and each term is given by a sub k. So this is the index of the summation. And then the lower number is the starting index, and the upper number is the last index. And so what this means is that I add all the terms starting from index equals 1, and I increase each index by 1 until I get to the last index. So for example, here again the first index is 1, so you have a sub 1. Then I increase the index by 1, so the next will be a sub 2, a sub 3, and so on, until I get to the last index, which is a sub n. So for example, if I have the sum k equals 1 to 4, a sub k, this is 4, sum equals k equals 1 to 4 of a sub k. So again, the first index is 1, and then I should go until index 4. So a sub 2 plus a sub 3 plus a sub 4. And so whatever value these terms have to calculate this sum, I just add all the terms up. So let's take a specific summation. So say sum k equals 1 to 4. So the terms are k squared. And so what I do is I plug in each value of k into the formula, and then I run from k equals 1 to 4. So when k equals 1, I get 1 squared. When k equals 2, you get 2 squared. K equals 3, you get 3 squared. When k equals 4, you get 4 squared. Right, so there's 4 terms, and then each time you plug the index into the formula, so you get this. And then so now I just add this all up. So this 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and if you add this up, this is 10 plus 20, which is 30. So the value of the summation is 30. Okay, so this is a quick review of sigma notation. Okay, so now on to the main topic, which is on infinite series. So an infinite series is just a summation where we let the index go to infinity, and it's written in the following way. So the sum k equals 1 to infinity. So in most examples we'll do the starting index will be from 1, but that doesn't always have to be the case. So the index can start from any number, even negative numbers. But then for an infinite series, we always let the index go to infinity. And okay, so this is supposed to represent a sum. So again, we start from the starting index, but now we imagine that there are infinitely many terms. So you go up to, say, sum a sub n, and you keep going on to infinity. So there should be infinitely many terms in the summation. So you might be thinking, if you're adding infinitely many things, this would be infinite, and there's not much to think about. However, similar to improper integrals, um, you can think of a lot of these summations in geometric terms, and if the contributions on all the later terms are so small that the total contribution is going to be finite. So as a quick example, let's look at the following infinite series. So the sum k equals 1 to infinity, 1 over 2 to the k. So let's write out the first few terms. So when k equals 1, you get 1/2. When k equals 2, you get 1/4. 2 squared is 4. When k equals 3, 3 squared, 2 cubed is 8, so you get 1/8. When k equals 4, 2 to the 4th is 16, so you get 1 over 16, and then so on. So these are the first 4 terms. And I can interpret this summation geometrically with the following picture. So suppose I take a unit square okay, so 1/2 would represent half of the square. The second term is 1/4, which represents 1/4 of the square. The third term is 1/8, so that represents 1/8 of the square. Then the fourth term is 1/16, so 1/16 is half of the remaining piece. That's 1/16 of the square, and then so on. So adding all of these terms up, so again, you imagine there's infinitely many terms, would be adding infinitely many of these pieces. But if I put all the areas together, you can see that you add up a smaller and smaller piece of the square, and so if we imagine this process going to infinity, it's going to actually cover the entire square, and so the total area is equal to 1. And so this series, if I were to add infinitely many terms, would be equal to 1. And so even though there are infinitely many terms, since each additional contribution is so small, the total is still a finite number equal to 1. So this gives some sense of how to interpret these series. Okay, so let's introduce some formalities so we can think about infinite series in general. So the idea is to make sense of infinite series, we basically add one term at a time, kind of like how I drew this picture, so one additional piece at a time. So to make sense of an infinite series, we add one term at a time and see if it approaches a unique value. So essentially this is what's called the sequence of partial sums. So in general, for a series such as the sum k equals 1 to infinity of a sub k, the sequence of partial sums which we'll call capital S sub n is given by, so each S sub n, so each term in the sequence is a partial sum going from 1 to n of a sub k. So for example, S sub 1 would go from 1 to 1, so that would just be a single term. So k equals 1, so that will be just the first term, a sub 1. And then S sub 2 is sum k equals 1 to 2, so this will have two terms. So it will be a sub 1 plus a sub 2. And then similarly, S sub 3 will be a sub 1 plus a sub 2 plus a sub 3. So basically, what we're doing is we're adding one additional term each time to get this sequence, and we look at if this sequence approaches a value to determine the value of the series. And so in general, we'll say that a series converges or diverges if the sequence of partial sums converges or diverges. Okay, so let's take a look at a couple examples. So let's look at the example we did above, and instead of interpreting it geometrically, we're going to do it this method, looking at the sequence of partial sums. Okay, so the series again is the sum k equals 1 to infinity of 1 over 2 to the k. So then the first few terms were 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. Okay, so the sequence of partial sums so let's calculate this sequence. So S sub 1 is just the first term, which is 1/2. S sub 2 is the sum of the first two terms, so 1/2 plus 1/4. Calculate this, this is 3/4. S sub 3, S sub 3 is the first three terms, so 1/2 plus 1/4 plus 1/8. If you add these three terms up, you get 7/8. And then S sub 4 is 1/2 plus 1/4 plus 1/8 plus 1/16. And again, if you add all this up, you get 15 over 16. So you can see that the partial sums is getting larger and larger, but they're always smaller than 1. Okay, so let's see if we can get a formula for the partial sums. So S sub n, so the denominator is always a power of 2, right? So here the denominator here 2 is 2 to the first power, and the index is 1. Here 4 is 2 to the second power, so that's 2 squared. 8 is 2 to the third power. 16 is 2 to the fourth power. So the denominator is 2 to the index. So the denominator is 2 to the n. And the numerator is always 1 less than the denominator. So the numerator would be 2 to the n minus 1. So this is the formula for the sequence of partial sums. And as n goes to infinity, so if we continue the sequence, it looks like this is getting closer and closer to 1. So we see that Sn goes to 1, Sn goes to infinity, and so the limit of this sequence is what we determine as the value of the series. And so the series converges to 1. Okay, so let's take a look at another example. So let's look at the series sum k equals 1 to infinity. One over k times k plus 1. Okay, so again, let's write out the first few terms. So when k equals 1, denominator is 1 times 2. When k equals 2, the denominator is 2 times 3. K equals 3, denominator is 3 times 4. Denominator is 4, the denominator is 4 times 5, and so on. So the first term is 1/2, second term is 1/6, the third term is 1/12, the fourth term is 1 over 20, again, and so on. So let's look at the sequence of partial sums. So S1 is equal to 1/2, S2 is 1/2 plus 1/6. So if you add it together, you'll see it's 2/3. S3 is 1/2 plus 1/6 plus 1/12. Again, if you add it together, you get 9 over 12, or 3/4. S4 is 1/2 plus 1/6 plus 1/12 plus 1 over 20. And again, if you add it together, you get 48 over 60, or 4/5. And so the sequence of partial sums, so the numerator is the same as the index, so the numerator is equal to n, and the denominator is 1 more than the numerator, the denominator would be n plus 1, and as n goes to infinity, you can see that the numbers are again approaching 1, so Sn goes to 1 as n goes to infinity. And so this series also converges to 1. Okay, so then this was a short introduction to series.